We have been talking about glycolysis. One thing that I don't think we've made the point of yet, or that none of you have mentioned yet, is that I told you at the outset we were going to make 2 molecules of ATP, and yet, so far, all the way through step, 1, 2, 3, 4, and 5, when we get to glyceraldehyde 3-phosphate, we've done nothing but consume ATP. So we lost 1 molecule of ATP there. I'm highlighting it in red because we're in the red. We lost a molecule of ATP, and then another one. So what's going on here? Isn't that a setback? Aren't we supposed to get 2 molecules of ATP? Well, it turns out we're going to recoup that investment, and we're going to make 2 additional molecules of ATP. So from glyceraldehyde 3-phosphate forward, we're going to make 4 ATPs. It's a little bit like the process, this kind of process is a little bit like trying to go over a mountain to reach a better valley on the other side. You got to go up before you can descend to the promised land. Or, I don't know, if you follow, as Lin-Manuel Miranda's Alexander Hamilton once said in the song, The Room Where It Happens, if you got skin in the game, you stay in the game, but you don't get a win unless you play in the game. Oh, you'll get love for it, you'll get hate for it, you get nothing if you wait for it. Nobody knows that? Okay, it's been a long time. Anyway, we have to invest those 2 molecules of ATP to commit the molecule of glucose to the process, and also to get the functional groups in the right place so that we can do some downstream reactions. The other thing I want you to pay attention to is, from this point on, from glyceraldehyde 3-phosphate on, after we've done the retroaldol reaction that made dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, all of the dihydroxyacetone phosphate becomes glyceraldehyde. And so for every molecule of glucose, we've got 2 of these. So every step from here on out, you need to count twice. In other words, here is a payoff. We're going to make NADH. That's going to happen twice. Here is payoff. We make ATP. That's going to happen twice. And by the way, at that point, we have paid off our debt. And then later on, we make another ATP. That's going to happen twice. So I'm just going to put 2x by each of these so that you realize that for each glucose molecule, everything from glyceraldehyde 3-phosphate on happens 2 times. All right, questions about how that balances out? All right, so we're going to start with this reaction, which is number 6. You start with an aldehyde, glyceraldehyde 3-phosphate, and from here on out, irrespective of whether the particular molecule came from glyceraldehyde 3-phosphate or dihydroxyacetone phosphate, from here on out, we're going to number the atoms 1, 2, and 3, starting with the aldehyde. So we start out with the aldehyde. We're going to use a molecule of NAD plus and a molecule of phosphate. This is just the conjugate base of phosphoric acid. A lot of biochemistry textbooks will call this inorganic phosphate, meaning not organic, meaning the phosphorus is not attached to anything, any group that has a carbon in it. Anyway, what we do in this process, if you pay attention to the aldehyde carbon, we're going to oxidize it from the aldehyde oxidation state, where we have 2 bonds to oxygen. It's bonded to oxygen, another carbon, and a hydrogen, to a higher oxidation state, again focusing on the aldehyde, on the carbonyl carbon. This has now got 3 bonds to oxygen and 1 bond to carbon. And remember, oxidation in organic chemistry can mean either a reduction in the number of CH bonds and or an increase in the number of carbon heteroatom bonds. So this process of going forward from the aldehyde to bisphosphoglycerate is oxidation. Okay? This is the oxygen that used to be, that's the aldehyde oxygen. Here it is as the carbonyl oxygen. Also, this functional group in which the carbonyl is attached to a phosphate leaving group is called an acyl phosphate. Do you remember what level acyl phosphates are? One, right? A carbonyl carbon attached to a good leaving group. That's level 1. Do you remember what level the aldehyde is? Also 1. So we're going to expect this reaction to be not very downhill because we're taking one highly reactive. We're going to expect this reaction overall to be pretty neutral because we're taking one highly reactive starting material and we're making a highly reactive product. All right. We need to talk about how this oxidation happens, and it would be useful ahead of time to focus on what's missing. So what do you notice about the aldehyde that is gone in the acyl phosphate? What's missing? Yeah, that aldehyde hydrogen, which I'm going to highlight in orange. The aldehyde hydrogen and its electrons are missing. The electrons in the bond between carbon and phosphate come from a lone pair on the phosphate, inorganic phosphate oxygen. So this hydrogen and the electrons in the carbon-hydrogen bond are now gone in the product, okay? Where did they go? They had to go somewhere. I bit my tongue while I was talking. That is annoying. They had to go somewhere, and the place they went is here to NADH. So we need to talk about how NAD plus is the thing that accepts the orange hydrogen with its electrons. The word for a hydrogen plus its 2 electrons is hydride, okay? So I got started and I didn't start a new document, so we'll just do that there. All right, so let's talk about how NAD plus can accept a hydride. You've seen the structure of NADH here. I told you that N stood for this nicotinamide group. D stood for these 2 ribose sugars that are in a dinucleotide linkage, and then A stood for this adenine base. But we're going to focus all of our understanding on this section of the molecule. So recall that you can abbreviate NAD+, which we're going to call an oxidizing agent, or alternatively, a hydride acceptor. And it looks like this. A nitrogen in a 6-membered ring where the nitrogen's bonded to an R group. There are 3 double bonds in that ring, one of them with nitrogen, and the nitrogen has a positive formal charge. There are a lot of hydrogens here that are implied but not shown. I guess I'll draw all of them just to make the point, and then I'll quit drawing them. And NAD plus has a resonance structure that you can get by pushing this moving this pi electron, these set of pi electrons from being in this bond between this carbon and that one to now being between these 2 carbons, and then moving this pi bond onto as a lone pair onto the nitrogen. If you do that, the original carbon here that was bonded to doubly bonded to the other carbon has to have a positive formal charge on it. It used to be surrounded by, it used to own 4 electrons, now it only owns 3. the lone pairs here. And just to be clear, the electrons from this pi bond end up here. The electrons from this pi bond end up here. And then of course I'm missing the amide group that's there, and I'm not showing the other hydrogens that are on the other carbons. So the point is NAD plus is electron poor. And the place that's ready and willing to accept the hydride is this atom that is opposite the nitrogen. These two are resonance structures of each other. So remember that when we talk about resonance structures, what we mean is each is an incomplete description of the overall molecule. You might want to say which one is right, and the answer is they both are right. Are the electrons actually hopping back and forth? No, they are not. What this tells you is the positive charge is simultaneously in more than one place. Okay? And one of those places, the most important of those places, is this carbon that I've highlighted in orange. All right? So that's going to be the atom that accepts the hydride. Questions about that? All right, let's look at your quiz, because your quiz is going to ask you to walk through this. And it's, rather than have me sort of give you the answer and then have you try to memorize it, I want us to look at it and see if we can sort of discover it together. And you've got structures of NAD plus and NADH there. Here I've shown you just the same step that we're talking about. Glyceraldehyde 3-phosphate goes to 1,3-bisphosphoglycerate. That's an oxidation of the aldehyde carbon up to a higher oxidation state. You can tell that because you've got more bonds to a heteroatom, as we explained. This is going to involve using NAD plus as an oxidizing agent. We've already said that we need to get rid of the hydride, the hydrogen with its electrons. And the thing that's really bizarre about this is essentially we're asking for the hydride to be a leaving group, which we know it absolutely isn't. H minus is a terrible, horrible, no good, very bad leaving group. You can tell because its conjugate acid is H2 or hydrogen, which has a pKa of 35, astronomically higher than anything we would consider to be a decent leaving group. But aside from that, if you look at what changes in this reaction, it looks for all the world like we got a nucleophilic substitution reaction, because in the place of the hydrogen with its electrons, we now have the phosphate group. It's almost as though the phosphate group attacked as a nucleophile, and then the hydride got eliminated as a leaving group. The only reason we know it's more complicated than that is we don't see H minus over here as a product of the reaction. And as I said, where is it? Well, it's right there in NAD+. It gets added to NAD+. So I'm showing you below intermediates in the mechanism. You don't have to figure this out on your own. We're going to work through the mechanism using what we know about addition, elimination, and deprotonation to come up with a reasonable mechanism. And we're going to have to use what we just learned about NAD+ as a hydride acceptor, remembering that it's this atom on NAD+ that is electron poor. Okay, so the first thing you got to know is that even though the phosphate group needs to replace the hydride, the enzyme mechanism uses something else. Go ahead.
So I have a question. With the NAD plus and the NADH, I know there was like ATP and ADP.
Yeah.
Does that just mean that we have both
It's a good question. So this circular arrow here, I could have, this is just a shorter, more compact way. I could have written NAD plus and put it here. And then I could have written NADH and put it here as a product. Biochemists sometimes do this to highlight that a reaction generates a molecule that people are interested in. So NAD plus is one of the two starting materials. It and this come together. You get 1,3-bisphosphoglycerate out and NADH out. Yep. And we'll do that for ATP and ADP as well. Good. Huh. All right. So one of the things enzymes do to accelerate reactions is they'll involve enzyme side chains in the chemistry. And you might ask, why couldn't it just be simpler? And the answer is, I don't know, only it must work faster when the enzyme's involved. So if you look, there are some important things that happen in this enzyme active site. Oh, and before I say that, this kind of enzyme is called a dehydrogenase or a dehydrogenase. Enzymes are typically named for the molecule or molecules they work on. That is sometimes called the substrate. The substrate of the enzyme is the molecule the enzyme acts on. So glyceraldehyde 3-phosphate is the substrate, and then dehydrogenase describes what it does. You will see in general that dehydrogenases do oxidation reduction chemistry, and we'll illustrate why it's called dehydrogenase in a little bit. Okay, so in the enzyme active site, there is a thiol-containing amino acid. That amino acid happens to be called cysteine. And after the first reaction, that it looks like that cysteine has formed a bond with what used to be the carbonyl carbon of the aldehyde. And there's a negatively charged oxygen on that carbonyl oxygen. So what do you think are the right arrows for this step? Where would you start? Enzyme B, the base, doing what? Removing the hydrogen. How do you know that that happened? Yeah, over here, the sulfur, go ahead, I heard something about a negative charge. Right, you need the negative charge on the sulfur to attack the carbonyl carbon. That's good. And you also know that it's happened because there's no hydrogen on the sulfur over here. Okay? So that's a deprotonation reaction. If you wanted to, if you were drawing this out yourself and had a lot of paper, you could go like this and draw the negatively charged sulfur, and then in a subsequent step, you could show that negatively charged sulfur attacking the carbonyl carbon. I'm just gonna go straight for it. Have the electrons in this hydrogen sulfur bond, then go to attack the carbonyl oxygen and get a tetrahedral intermediate. We attack, again, so much of what we've done so far with carbonyl chemistry is, the LUMO is the carbon oxygen pi star. When the nucleophile attacks the carbon oxygen pi star, you must break the pi bond, and that's where we get to this intermediate. You can also tell that the base removed a proton because here is its conjugate acid over here. Some people, as they draw mechanisms, are not going to be that thorough. They're going to do the deprotonation and then they're going to forget to draw this. You'll have to forgive them for that. It'll happen. But I drew it here for completeness because I know it's helpful to see what's gone on. All right, any questions about that step? What two of our three fundamental reactions are included in that step? Deprotonation, and what's the other one? Addition. Great. Now, here's maybe the tricky one. The starting material here is this tetrahedral intermediate. Here is the hydrogen that we know has to be gone in the product. And here are the electrons in its carbon-hydrogen bond. I told you that NAD plus is an electrophile. Looking at the products, we have changed from this tetrahedral intermediate to a thioester, where the sulfur nucleophile is now attached to the carbonyl carbon. And it looks like our hydride was delivered straight to NAD plus to give us this molecule NADH. Okay? So, what arrows do you think I'm going to need to make this happen? Great. Oxygen kicks down, and you're using that why? Great. You want to make the pi bond, and you want H minus to leave. Right? Now, there's a difference between H minus leaving like this. If I draw that arrow, what I'm communicating is that H minus is swimming around in biology. That actually doesn't happen. H minus does not last long at all in water. It forms hydrogen gas and it's exothermic enough to start a fire. Are you currently on fire? Metaphorically in your brain, sure. But you are not currently on fire. So what that means is your body is not actually letting hydride swim off on its own. If you go look at the enzyme active site, what happens is NAD plus gets up really close to that hydride so that it gets handed off directly like a relay race. H minus is never on its own. All right? So we'll show the arrow from the orange bond, that carbon-hydrogen bond, is going to break, and hydrogen with its electrons are going to make a new bond here. To accommodate that, I've got to do this. Alternatively, if you prefer, you could have done this from the other resonant, oh man, I screwed up. If you could have done this from the other resonance structure of NAD+, that is, you could have just drawn the plus charge there and then had this arrow go straight to the plus charge and you'd be done. Yes?
When you're drawing resonance structures, do you have to follow the octet rule for all atoms?
When you're drawing resonance structures, do you have to follow the octet rule for all atoms? The answer is it's better if you do. Atoms can have less than a full octet, they can't have more. So a positively charged carbon is okay. It's not as good as a structure where the carbon doesn't have a full octet. But what we would say is this is a minor contributor to the overall structure of the molecule, and that this carbon is a little bit electron poor.
Okay, and we're focusing on that type of resonance because of this hydrogen with its electrons.
Right, yeah, it's easier to see why the hydrogen goes here if you know about this resonance structure. In the same way that it's easier to see why a nucleophile attacks a carbonyl here at the carbonyl carbon if you know about this resonance structure. In other words, minor contributors with positively charged carbons sometimes tell you a little bit about how the molecule reacts. All right, good. Other questions? Yeah.
Just like for resonance, we learned that these like have a lone pair and a double bond adjacent. On the left, where is the lone pair?
So resonance can occur anytime. I taught you one situation where resonance can occur, and that is where there is a lone pair adjacent to a pi bond. It's easier to see that here. Here is the lone pair, and here is the pi bond that it's adjacent to, and then I can move them over like that. Okay, couple other things about this step. The carbon molecule gets oxidized, and NAD plus is the oxidizing agent. It's the thing that receives the hydride. You can tell that the thioester is oxidized relative to your starting material because it has one fewer CH bond. Similarly, you can tell that NADH is reduced. How can you tell that? It has one more CH bond. We could also call our intermediate here a reducing agent because it's the thing that delivers H minus to NAD+. So in an oxidation reduction reaction, you can't just do one thing. One thing gets oxidized, the other thing gets reduced. The oxidizing agent gets reduced, the reducing agent gets oxidized. It's always coupled in that way. Okay? All right. So now we've accomplished part of what we set out to do, which is we oxidized the aldehyde to a thioester. And we expect that to be, again, pretty level 1, pretty neutral, because you're going from a level 1 aldehyde to a level 1 thioester. Now, we simply want to replace the thioester with a phosphate. So now you know that thioesters are reactive because RS- is a decent leaving group. Now we're going to use phosphate as a nucleophile, and we're going to do what looks like addition and elimination to get nucleophilic substitution at the carbonyl carbon. So looking where we're going to end up here, what does it look like the phosphorus lone pair on the oxygen has to do? Got to go for the carbonyl carbon. Break the pi bond. Why do you break the pi bond? Because the LUMO is the pi star, the carbon oxygen pi star. That gets you to this tetrahedral intermediate. There's what used to be the carbonyl carbon. There's what used to be the carbonyl oxygen. Here is the sulfur, and here is the phosphate. Now this is an interesting intermediate because you can imagine either of those being good leaving groups. It's about the same in energy to kick off the thiol as it is to kick off the phosphate. So you expect this step to be reversible, and it is. If we kick off the phosphate, we go back to the previous step. If we kick off the sulfur, we go forward to the desired acyl phosphate product. Now, if you look at what we've got over here, what does it look like happens to the negatively charged sulfur as it's leaving? Protonation, yep. So this is one of these combined elimination and protonation steps. If you wanted to show SR minus leave first and then in a subsequent step have it pick up the proton to become neutral again, that's certainly fine. And this then gives you your 1,3-bisphosphoglycerate acyl phosphate. This reaction generates a molecule of NADH, which, remember, anytime you see us generating NADH, you need to be thinking, hey, that's sweet because I can exchange that for ATP, for 2.5 ATPs in the electron transport chain. The other thing this reaction does is it sets us up to be able to make ATP in the next step. All right, any questions you have about that mechanism? Yeah.
What would a test question look like?
What would a test question look like? Well, I suppose it might look like this. I show you this reaction, and then I show options A through F or something like that, and I actually show you intermediates with arrows. They may or may not be in order, A through F, and I ask you which of these is not correct, or which of these is not does not work. And there are two ways I could do that. I could make an incorrect answer by showing you arrows that don't make sense or that are wrong. A classic example of that would be supposing, this is just a dumb thing, but messing up how to show a proton transfer reaction. The arrow always starts with the lone pairs, never with the proton. So that's an example of something that would be wrong. Another thing that would be wrong would be to show you an incorrect structure. So supposing you would need to know that you start with glyceraldehyde 3-phosphate. So just off the top of my head, a way to show an answer that wouldn't make any sense but would look reasonable would be to have this phosphate group on the wrong carbon. So then you'd have to have some memory of what the right intermediates are, some understanding of it in order to get things right. So there's a couple of ways you can do that. Alternatively, I can have options A through F all be bogus except for one, or maybe a couple of them. And when there's multiple answers, as you've seen, I will say that in the question. Yeah.
So on the second intermediate, could you show the homo on that, on what's happening there with the lone pairs coming down?
Yeah. So the HOMO would be lone pairs on this oxygen. And what's unique here is the thioester is a better leaving group than H minus. So some of the time at least, the thiol gets kicked, the thiol is a better leaving group. Some of the time at least, that thiol gets kicked right back out and we go to starting materials. If NAD plus is sitting there to catch the H minus, that suddenly makes H minus a better leaving group. So yeah, what is happening is lone pair electrons on the oxygen are dumping themselves into the anti-bonding sigma star between the carbon and the hydrogen. That so that you can break that bond.
And that can only happen because
And that can only, otherwise, the presence of NAD plus must make that anti-bonding orbital low enough in energy to break. Otherwise, there's no way. Yep. All right, others? Okay, you're gonna see examples of this kind of thing, an NAD plus mediated oxidation, all the time in metabolism. And every time we do, you need to think that's one step closer to CO2, and that's 2.5 more ATP molecules that we just made. All right? Great. So let's talk about the next step after that. This is a step where we regain some ATP. So you start with bisphosphoglycerate, you make ATP, and you end up with 3-phosphoglycerate. So I'm going to draw this out on notes so that we can understand it a little bit better so you can see what's going on. The name bisphosphoglycerate comes from, I think, Greek descriptions of how many of something there are by for two. Bisphosphoglycerate means there's 2 phosphate groups, though as you can see they are not the same. This one is a phosphoester and this one is an acyl phosphate. 1,3-bisphosphoglycerate. And the interesting thing about acyl phosphates in general is that they have multiple possibilities for the atom that gets attacked. I'm going to show a couple of different ways to consider an acyl phosphate. So one is to think of the phosphate group as the leaving group, and the carbonyl carbon as the electron poor carbon, and the carbonyl oxygen is where the negative charge is going to go after an addition reaction. And that's great because the reason it's reasonable to think about that is because the leaving group has a conjugate acid. I guess I should just move this somewhere else. The phosphate leaving group has a conjugate acid, which is the phosphate monoanion, and its pKa is 7.2 or something, close to that. So that's a decent leaving group. But you can also, at the same time, think about the acyl phosphate with the phosphoryl group as being the electron poor group and the carboxylate as being the leaving group? What if this is the leaving group and this is the electron poor atom that gets attacked, and that's the oxygen that receives the electrons? If that occurred and the carboxylate left, what would it look like? Like that. Of course, the carboxylate's conjugate acid is a carboxylic acid, which has a pKa of 4. So the genius of an acyl phosphate is that it's reactive on both the carbonyl carbon and the phosphoryl phosphorus. And you won't necessarily know which to expect to react unless you know what the reaction's going to do. And if we go back and look at what the reaction happens, you should be able to infer which gets attacked, the carboxylate carbon or the phosphorus. So let's take a look at that reaction one more time. This phosphoglycerate reacts with ADP to give ATP and phosphoglycerate. Which of these atoms, the carbonyl carbon or the phosphoryl group, do you think gets attacked? Has to be phosphoryl. You can tell that because on the other side, the carboxylate's the leaving group, right? Which is why I went and redrew it. I drew the molecule this way with carbonyl and leaving group so that you could compare that to the aldehyde. But now, in the next reaction, you're going to see that it's the phosphoryl group that's the electron poor thing that gets attacked, and the carboxylate's the leaving group. So let's just show that happening. To do that, I'm just going to highlight the carboxylate in green. That's our leaving group. If you want, you could do the whole thing. The electron poor phosphorus is in blue, the oxygen's in pink. Our nucleophile in this reaction is going to be ADP. And by ADP, I mean one of the oxygens on the beta phosphorus of ADP. And understand that in most reactions that are involving ADP, magnesium is present as a cofactor to help neutralize the highly negatively charged molecule. All right, so all of this is our nucleophile. And as we've numbered the atoms, this is the alpha phosphate group of ADP. This is the beta phosphate group. And preview, this one here is going to become the gamma phosphate group. So what do you expect? What should I do with the lone pair electrons on ADP? Attack. Attack who? The rebels. No, the phosphorus. Break the phosphorus oxygen pi bond again because the LUMO is the pi star. That's going to get you an intermediate. I'm going to now use abbreviation freely so that we don't have to draw as much. Here is the oxygen from the beta phosphoryl group of ADP. And I'm just going to put an R over there on that side to make it a little bit easier. This is the carboxylate leaving group. This is the phosphate that got attacked. This is the negatively charged oxygen. This is the alpha, the beta, the gamma phosphates. An elimination reaction happens next where electrons on the oxygen kick down and the carboxylate leaves, and boom, we get 3-phosphoglycerate, which I'm just representing as this, but the structure is shown on your handout, and then ATP. All right. What level was this acyl phosphate that we started with, bisphosphoglycerate? What level would you put that at? numero uno, right? How about ATP? Also level 1. So part of the genius of glycolysis is we arrange the functional groups to the point where we can generate a molecule of ATP totally reversibly because our starting material is so high in energy. All right. All right, questions about that step? At that point, our debt is paid, but we've made a molecule of NADH, so now we're actually ahead of the game. But there's still a few more, there's one more molecule of ATP we can get out. Anything else you want to say about that one? Yeah.
So you said that our debt is which step again?
The debt we paid was, the debt we incurred was from step 1 and step 3, where we consumed a molecule of ATP.
And then it's repaid right here.
It's repaid here because we have 2 molecules of glyceraldehyde 3-phosphate that go through this reaction twice to give us those ATPs back. And then you'll see if you follow along, in the end, at the very last step, we're going to get 1 more molecule, 2 more molecules of ATP, and therefore come out ahead. Yeah?
When you say consumed, do you mean metabolized, or you just mean not?
I don't mean totally destroyed. I mean we went from ATP to ADP. And that the reason I'm using the term consumed, because when your body makes ATP in the electron transport chain, it's literally taking ADP and tacking a phosphate on there. And so anytime you use an ATP, that's like, oh man, that's got to go back over there and get phosphorylated again. Yep. Okay, any others? All right, so after we get 3-phosphoglycerate, nature moves the phosphoester. You start with a phosphoester on the C3 oxygen, and in the product, the phosphoester's on the C2 oxygen. So this reaction is reversible because you're just exchanging one phosphoester for another. Probably there's some charge repulsion as the phosphate gets closer to the carboxylate, and probably you've got a magnesium counterion helping out with this kind of thing. The mechanism here, I'm not going to show you. It is known. It's not particularly important for what we want to do. I'm just going to describe it as phosphoester exchange. What nature does is the enzyme that does this reaction, phosphoglycerate mutase, will actually put a new phosphate group on the 2-hydroxyl and then remove the old phosphate group from the 3-hydroxyl. And how that happens, it doesn't actually need ATP. It's an enzyme that already has a phosphate group on it attached to a decent leaving group. We could look at it, it just really wouldn't add a lot and probably would add some confusion. It's just not worth the pain. So, is that all right? If you want to see it, you can come talk to me and I'll show you the step. A little bit about enzyme names. Notice that the previous step we talked about, which is where we regenerate ATP and pay our debt, is named according to first what the substrate is, and second what it does. The substrate is phosphoglycerate, and what it does is a kinase. Now you can see clearly that it's named for the backwards reaction, because when we're doing this reaction in the forward sense, we're making ATP. The kinase uses ATP to transfer a phosphate group to something. So phosphoglycerate kinase in that forward reaction sense, if you start with phosphoglycerate, the kinase would put a phosphate from ATP on the carboxylate to get 1,3-bisphosphoglycerate. I'm not sure that's making sense. Does it? I mean, it's named for the backwards reaction. Do you want to ask some clarifying questions before I stumble over myself even more?
Is that extremely important to know?
I mean, you need to know the enzyme name, so that'll help you remember them. Okay, this one is named for, again, the substrate, phosphoglycerate, and what it does. Mutase is something that moves a group, changes the location of a group. You might think, oh, does it mutate something? Well, it doesn't mutate any organisms or DNA, but it does move where a group is. All right, 2 more reactions. And the 9th one is also a feature of your quiz, which I think we'll look at now. But actually, yeah, let's just take a break now before we do that. Let's just pause, take 5 minutes, and then we'll finish up.